All right, guys. So section 3.1 is called linear models. Here you're going to get some word problems. And this deals with growth and decay. And we're looking at this differential is the normal setup that we want, where you could see now is with respect to time or t. Okay, and here's the first example. So one thing with this, right, this statement here has to do with your initial value. So whatever they're giving you, and you could see even in the word problem, they say time equals 1. The number of bacteria is measured to be 3/2 of the initial value. So you got to kind of look at notation as what they're given. This P sub 0 is the population of the bacteria at time equals 0. So when you first start looking at this problem. And then they say the rate of the growth is proportional to the number of bacteria P of T at a present time T. Determine the necessary time necessary for the number of bacteria to triple. So this is the setup. This is kind of like if you go back to algebra 2, it's a direct variation where you have direct variation was always y equals kx, right? So think of like if you work more, you make more money, that type of relationship. So in this problem, I'm going to start with something very similar where I'm going to have, since it's proportional to the bacteria P, I'm going to, instead of use X, I'm going to use P. So I'm going to do this, dP over dt equals K times some function P, okay? Now think about our, how do we get that original function? How do we find a solution, general solution for that? Separate and integrate. So dP over P equals K dt. Now I usually leave the constant with the X or the independent variable. In this case, T makes it a little bit easier. So from here I can say, okay, well I know ln absolute value of P is going to equal KT plus C, right? So you wind up, when you raise it to the E, right, ET plus C. And then just remember like that plus C is really EKT times E to the C. And again, just going back, that's still going to be constant. So now I'm just going to write my equation as C E to the KT, right? So we have this general solution to our differential that I have here, okay? Now, if you want to use linear, that's fine too, but you could also separate and integrate, but this is also, you could done by doing the linear process. So let's go back to this P equals C E to the KT. And if you notice, the two things that are missing in our solution is what is our constant K, constant K, and what is our constant C. So in order to do that, you go back to what's given, right? Here we have an initial value, okay? And we know, so I could write it this way, like, so P of, actually, P of 0 is going to give me P naught, okay? So that's your initial value. So with this, we could use that to find C, because let's say I plug in and I say, okay, P naught, right, is going to equal C E to the K times 0, right? So that K times 0 is just 0, E to the 0 is 1. So I got P naught is going to be my constant. So now I have my new equation. Okay, and so that's how we could find C is using that initial value. Now, in these problems, they're going to give you some other information, and we have our other information is that time equals 0, right? We have the population to grow 3/2 of that initial value. So I have another point that I could write. P of 1 is going to be that 3/2 P naught, or P sub 0. I always say P naught. Okay, so we could plug this in, right? I'll have 3/2 P sub 0 equals P sub 0 e to the k times now 1. All right, well, this is nice. Let's solve for k. So I cancel out, right, my P sub 0s. I have 3/2 equals e to the k. And now when you solve this, right, you have ln of 3/2, right, is going to equal k. So now I could rewrite that back into my equation here, where I have P equals P sub 0 e to the t times ln 3/2. Okay, well, we could even simplify that further, where I have P, right, and let's say I write it like this, 3/2 raised to the t. I know it's going to be e and ln are inverses, so I have this notation here. Okay, so with all that work that we have done, now we could use this to see, all right, well, determine the time necessary for the bacteria to triple. All right, so if I do that, what does that mean? It's going to triple. So I have 3P naught would mean that it triples the initial, and then I have it written like this. Cancel, cancel. 3 equals 3/2 t. All right. Just move this out of the way. All right, so going back here. How do we solve this now? We have 3 equals 3/2 raised to the t. Okay, well, I'm going to do ln to both sides, because in this situation I can bring down that exponent using our rules, right? So you have t equals ln 3/2. All right, and then my next step, I can do divide by ln 3/2, divide by ln 3/2, and I'll get ln 3. Oh, so if I did that in the calculator, sorry, I got 2.71 approximately is equal to t. All right, and this would be in hours. Okay, so you could see that that's the amount of time it will take for the bacteria to triple. Right, and that will be your first example for 3.1. Okay. All right, this is a half-life problem. Okay, so in a half-life problem, we have to find out the half-life. All right, so if you look at this, a breeder reactor converts relatively stable uranium into an isotope plutonium. After 15 years, it is determined that 0.043% of the initial amount of plutonium has disintegrated. Find the half-life of this isotope if the rate of disintegration is proportional to the remaining amount. So I mean, however you want to do this problem, still very similar, where we know we'll have, I think the book uses A over dt equals k times A, again because it's proportional to the amount remaining, and A of 0 is going to be our A sub 0, right? So you're still doing the same thing here, where you have an initial value and you have your rate, which is proportional to the remaining value. So the way I'm going to write this is, we could still use, now you're always starting out with this notation here, right? And if you notice, it's always going to wind up being this after you solve for a general solution. In our situation though, we have A, so A is going to equal C e to the kt, and then our initial value I'm just going to replace. So A naught is e to the kt. Now let's go back up to the problem. After 15 years, right? So in this case, t is going to be written in years because that's what's given. So I'm going to say A of 15 is going to equal 0.004. I think I need another 0 though, right? Oh, and I'm wrong about that anyway, because it says of the initial value. So before I do that, the 0.043 has disintegrated. So let's do it this way, where we do 100% minus this 0.043, just to see how much is remaining from that. And that came out to that 99.957%. So I could write this as 0.99957 of that initial value. Okay. Okay. So let's use that to find out what the k is. So I'm going to have 0.99957 of A naught is equal to A naught e to the kt, and now I could solve for k. Right, so I'll have 0.99957 equals e to the kt. Wow, you know what I forgot to do? Put in the 15. Sorry about that. Okay, so you have, because this is at 15 years, right? This is at 15 years. And then we could do ln of this value equals k times 15. All right. If I divide by 15, I'd get a decimal that looks like negative 0.00012340287. Okay. I know there's a lot. Let me move this down. With this is you're going to get decimals, but just try to stay consistent. I don't want to round too much because I want to use the whole thing. Okay, so I'm going to write this into our equation. Okay, so here I'll have A equals initial value A naught, and then times e to the 0.0002867t. And this is the equation we want to use. And now what they're asking is find the half-life of the asymptote if the rate is this integrated is proportional to the amount remaining. So now half-life. So when you're setting up half-life, you're trying to say, okay, A of what time is going to give me 1/2 that initial value. So I'll have 1/2 A naught equals A naught e to the negative 1 point, and then this whole long decimal times t, right? So you could see this will cancel. I have 1/2 equals this e to the negative 0.000287 t. Now we could do ln to both sides. And if I divide by that big decimal, okay, I get t to equal approximately 27,180, and we had it as years, right? If I remember correctly, years, yes. Okay, so that's a half-life problem, all right? And this is the notation. Whenever you're talking about half-life, it's half of what is remaining, okay? So we'll get that. All right, the last example I want to do in 3.1 is a cooling, so Newton's law of cooling. So whenever you're thinking of cooling or warming, right, you're using this Newton's law. And I think many of you probably know that if you took any like science class. But for us, really the differential that you want to use is whatever we're talking about here. So I'm using temperature. So you have a capital T, just be careful of the capital and the lowercase t. And again, it's going to be proportional. You're going to have some constant, and then the temperature minus T sub m. Okay, so T sub m is always a constant. And this is always going to be whatever the atmosphere is, so the ambient temperature, meaning the room temperature a lot of times. Okay, it's just whatever the temperature is in that room or vessel or wherever we're talking about. Maybe it's in an oven or something. Okay, so everything else is the same. So before we get to doing this problem, you see this cooling of a cake and we want to use that. So what I'm going to do first is just get a solution for this differential. So you're still doing separate and integrate, right? And then we integrate both sides and we would get ln t minus t sub m equals k lowercase t plus c. And again, we have the same situation here where it's e kt plus c. And so c, so I'll have t minus t sub n equals c e to the k t. And if you're solving for t, you'll have this notation every time. Okay? Just remember, like t sub n, this is going to be given as far as like a room temperature type thing. Okay, you're still going to have to find the constants there, but everything else will be the same. So anytime you see this, you're still using what we have with that Newton's law, but you're separate and integrate. You could use linear as well. It doesn't really matter. You could rearrange it so that it's a linear equation. Okay, so now with this, let's go back to the word problem. So when you're reading through, it says when the cake is removed from the oven, all right, you have an initial temperature, so it's going to be T sub 0 equals 300 degrees, okay? And then they say T of 3, so now our T is going to be in minutes. T of 3 is going to be 200 degrees Fahrenheit. And we're looking to see how long, right, what time is going to go back to room temperature of 70 degrees Fahrenheit, okay? So anytime you see room temperature, that goes in for your T sub M. Okay, so now let's see if we can find the other two constants. So I'm going to go with the initial one. Initial is 0, so I got 300 equals C e to the k times 0 plus 70, right? So that's 300 equals C e to the k. That's going to be just 1. I don't need that. Plus 70, so I get 230 equals C. All right, so let's plug that back in. Okay, next step. We're going to use this next value to find K. So I got 200 equals 230 e to the k times 3 now plus 70. So we'll subtract. I get 130 equals 230 e to the k times 3. So I have 130 over 230. Okay, if we apply ln, right, of 13 over 23 is going to equal to k times 3. And then ln of 13 over 23 divided by 3 is equal to k, which we'll write as approximately negative 0.9018 is approximately k. And now I have my equation where it's going to be T equals 230 e to the negative 0.19018 t plus 70. All right, so now we want to know, let's go back to the problem, how long will the cake cool off to room temperature of 70 degrees? So I'm going to plug in 70 and solve. So if I subtract, I get 0 equals 230 e to the negative 0.108018. And now 0 equals this. Couple things here that you can notice. Will e raised to anything be 0? No. Even if you did ln of 0, you would get an error. Okay. So since this is impossible, you would get no finite solution. We know that in this situation of the cooling, right, the limit as t goes to infinity, right, would approach 70 degrees, okay? So after a long period of time, then of course it would eventually go to 70 degrees. But in this situation, you would say that, the model itself isn't really realistic in the sense that eventually it would probably go to the room temperature that you want. But when you're solving an equation like this, you can't have that. Now, having said that, you could find out, okay, when is that going to be 80 degrees, and you would get a time because it wouldn't wind up with that no finite solution, and you would have this notation here. Okay, so that's 3-1.